Welcome back, calculus students. This is part 3 of the video notes for infinite limits and curve sketching using infinite limits. For this portion, we're going to be talking about transcendental functions and end behavior. So these are functions that either go to infinity, such as the logarithmic and the exponential, or don't have a limit as x approaches infinity, such as sine, cosine, and tangent. So the first example, we're going to find the limits as x approaches infinity and x approaches negative infinity for f of x equals 2 plus 3e to the x over 7 minus 5e to the x. First thing we want to note is if we took the limit as the function is written, 2 plus 3e to the x, 7 minus 5e to the x, we would get 2 plus infinity, since exponential functions approach infinity, and over infinity. And so that is not helpful to us, does not really let us know what our limit is. For this example, we want to use a similar strategy that we did to the rational functions, where we factored out a common factor to make the function rational. So basically, we're looking at our e to the x's, and we kind of want to factor an e to the x out of every term. So instead of doing this, we're going to say that this limit, and I'm going to take it all the way over to the left, is the limit as x approaches infinity of 2 over e to the x plus 3 over 7 over e to the x minus 5. And that's taking out the e to the x term from each term. So here, as x approaches infinity, we know that e to the x approaches infinity, which means 2 over infinity should approximate 0 for large values of x. And we've got 0 plus 3 over, same thing happening on the bottom, 0 minus 5. And then we can see this limit is equal to negative 3/5. Okay, let's approach this limit from the other side. So now we want to evaluate the limit, and I kind of want to keep the graph in my viewing window. We want to take the limit as x approaches negative infinity for the function 2 plus 3e to the x over 7 minus 5e to the x. And so we want to think about this just as our exponential functions alone. So if you look at the graph, e to the x as x approaches negative infinity approaches the horizontal asymptote of 0. So limit as x approaches negative infinity of e to the x is equal to 0, which means, using our limit laws, the limit as x approaches negative infinity of 3 times e to the x is also 0, which tells us that if we do the limit as x approaches negative infinity of 2 plus 3e to the x, we're basically just going to get 2 plus 0. And in the denominator, we're going to get 7 minus 0 using that same logic. So over here, we can see that the function will approach the horizontal asymptote of 2/7 as x approaches negative infinity. Moving down, we are finally going to get into the graph sketching portion of these notes. Now keep in mind you have graphing calculators and other tools to sketch the graph, but we're really looking for the application of this calculus-based problem-solving strategy for sketching a graph. So this is what I'm looking for when you sketch a graph in calculus. You need to determine the domain and any restrictions on the domain, locate the x and y intercepts, evaluate the limits at infinity and negative infinity, determine whether the function has any vertical asymptotes, calculate the derivative and locate the increasing, decreasing intervals as well as the extrema, and then calculate the second derivative to determine where the function has concavity and inflection points and maybe solidify your understanding of the extrema. And that's a lot. So let's go through that process for quite a few examples. The first example, and I'm really looking for justification, right? I don't need the graph. I need the justification of how the graph follows from each of these understandings and analyses and processes. So step 1, I know that this is a polynomial function. By looking at the degree, I know that this function is approximately a cubic. And then since the leading coefficient is positive, I know that it is odd positive. That means the overall behavior of this function is that as x approaches infinity, so does f of x. And as x approaches negative infinity, so does f of x. I also have an unrestricted domain when I'm talking about a cubic function. So the domain is equal to all real numbers. Next, I want to locate the x and y intercepts. To locate the y-intercepts, I'm going to plug in 0. And I'm going to get -1 squared times 2, which is +2. The x-intercepts are the zeros of the factors, so what can I plug in to get 0? And so I know that the x-intercepts are +1 and -2. And so I'm going to start my sketch before I run out of space to do so. So I've got 0, 2, 1, 0, and -2, 0. And I know that odd positives end up and begin down. So that's what I have so far with the information that I've determined. Next, I'm going to evaluate the limits at infinity and negative infinity, which I've actually technically already done up here when I talked about the end behavior. So we can skip that step. We're going to determine if it has any vertical asymptotes. It doesn't because it's a polynomial. Then we're going to calculate the derivative and locate the increasing, decreasing intervals as well as the extrema. So with the way the function is written, to calculate the derivative, I am going to be using the product rule. I could, however, take the time to distribute all the terms out if I wanted to, and look at this as a cubic polynomial instead of in its factored form. So with the product rule, I'm taking a look at the derivative of the first function, which I'm going to box in red. And so that derivative is a chain rule. We have 2x minus 1, and then the derivative of the inside is just 1, so there'd be an additional times 1. And then that's going to be multiplied by the second function, x plus 2, plus the derivative of the second function is just 1 times the first function, unchanged. Again, how you choose to simplify this is up to you. I'm going to try to take the path of least resistance, we'll see, and I'm going to factor out an x minus 1. So that's going to give me x minus 1, and that'll whoop, whoop. So I'm left with 2x plus 2 plus x minus 1. So those are my leftover terms, 2x plus 2, x minus 1. And that's going to break down to 2x plus x is 3x. And then feel free to pause the video so that you can approach this algebra in a way that's comfortable for you. One thing I like about using this method with factoring is that I leave my answer in factored form, which makes it a little bit easier to decide the zeros, the critical points, and the positive, negative sign chart. So this last step I did down here is I just factored out that 3 that the second term had in common, the second factor had in common. So what this tells me is that I have critical points at 1 and -1. So I am going to create a sign chart using 1 and -1. There are no restrictions on my domain, so I can choose any values I want to evaluate this. I'm going to choose -2 and 0 and +2, and I'm plugging these into the to the derivative to decide if the derivative is positive or negative, which will tell me if my function is increasing or decreasing. If I plug in -2 right here and here, I am going to get a negative times a negative, which is a positive. And this tells me that my function is increasing until -1. So over here, now I don't know where this point goes, so I'm not going to go too far. I know that's increasing. When I plug in 0 to these two locations, I get a negative times a positive, which is a negative. So I know in between -1 and 1 that the function is decreasing. But again, I don't know how high up it goes, so I'm not quite comfortable sketching that in. And then finally, if I plug in 2, I get a positive times a positive, which tells me that after this point at 1, and since I have this point at 1, I feel fairly confident that I can increase from there. So this leaves me with the question, I know that there's a max at -1, and I know that 1 is a minimum, but I don't know where this maximum is. So I'm going to take -1, and I'm going to plug it back in to my original equation up here. -1 minus 1 squared is -2 squared, which is 4, and -1 plus 2 is 1. So now I know that this maximum point is at -1, 4, and I need to extend my graph. So here's 2, 3, 4. That point is -1, 4, and then I can go increasing up to -1, and then I can go decreasing. Make sure you cross your y-intercept down here. And it actually looks like I've completed the graph, but let's just identify those inflection points because the concavity of this function definitely changed. It was concave down on the left and concave up on the right. So somewhere in between, it needed to switch. Last step for this process is to calculate the second derivative. F double prime. I could do this with a product rule again. I actually think I will do it with a product rule again. Although this one, no, I won't. Because this one's pretty easy to multiply. I know that x minus 1 times x plus 1 is x squared minus 1. So I'm going to go ahead and multiply that out. 3x squared minus 1. Take the derivative. You're going to get 3, 2x. The 1 will go away because the derivative of a constant is 0. And that tells you that the second derivative is 6x, which means the inflection point occurs at 0. And since the function is just 6x, I know that for all of the values less than 0, my function is concave down. And I know for all of the x values bigger than 0, the function is concave up. So this right here, 0, 2, is also my inflection point. I'm going to call it IP on the graph. So here's how we take a calculus approach to sketching a graph. For the last portion of the video notes, we're going to apply this to a variety of different and more complex functions.